Okay, so I said there's only gonna be 2 videos. Sorry, I lied again. There's actually 3. Second video is pretty short. 6 and 6.2. I mean, it's just too. So sorry. There was some stuff in section 6.1 we hadn't finished. So that was the stuff about specifying plus C in the previous video. And that plus section 6.2 is just too much to get into an entire video. It would be well over an hour. So hopefully you're starting to get a sense from the last video of how you might want to use indefinite integrals or antiderivatives in general. And now we're going to talk about the definite integral, which is basically builds further on the indefinite integral, and how this can be applied to study rates of changes in functions from knowing something about the rate of change. So this, in the last example, in the last video with the flu epidemic, we computed the people who had the flu at a given time t knowing the rate of change of flu. So this is we're going to expand upon that type of idea in a lot more detail in this video and the next few weeks as well. So definite integral and the net change of a function. Okay, so here's the setting. I'll start with a general setting. We'll play with some computations to get a feel for it, and then we'll do some examples, and you can kind of see how things will work in applications towards the end. Okay, so here's the idea. So suppose we have a continuous function, little f of x, and that capital F of x is an antiderivative of little f. Of little f of x, i.e. capital F prime of x is little f of x. Okay, so I'm just going to make it kind of an abstract definition, and then maybe we'll explain what it means. So then the net change, then the definite integral, so I'll do the definite integral first, of little f of x is, so we underline this, definite little f of x, from, skipping one piece of thing, from x equals a to x equals b is the following quantity. It's written with the integral sign, but you put a little a on the bottom and a little b on top. Fx dx is the value of the antiderivative capital F at b minus the value of the antiderivative capital F at a, and this is sometimes abbreviated as f of x bar ba. Okay, so there's a lot in this formula. A really important formula. Okay, so the definite integral is this guy here. So definite means it gives you a definite number instead of indefinite, which we did before, which gave you like a whole family of functions that all differ by this constant plus c, right? So you have a to b fx dx. And now let me explain what the language is here. So the values x equals a and x equals b are called the limits of integration. And the one that appears on the bottom is called the lower limit. So the value x equals a is called the lower limit of integration. And the value x equals b is called the upper limit of integration. Okay, so what this is saying is that this definite integral fx dx from a to b is the difference of the antiderivative capital Fx at b from the difference of the antiderivative capital F at b and at a. So, and that's abbreviated by, this difference is abbreviated by f capital Fx b ba. Okay, so notice, so just some remarks. Okay, so the difference, like I was saying, the difference f of b, so the value of capital F at a minus the value of capital F, the value of capital F at b minus the value at a is abbreviated by the symbol, the notation, capital F at x bar ba, okay? And this value, this difference, this is probably the most important thing, represents the net change in the function capital F at x as x goes from x equals a to x equals b. So this creature, this integral creature, takes what it does in some sense is it takes this little f and it produces out of it the net change in the antiderivative capital F. And this capital F, I should emphasize, this capital F is actually not just an antiderivative, it's any antiderivative. So no matter, this formula holds no matter which capital F you choose, or which antiderivative you choose. And that's, you can explain why this is true in the live meaning, but basically any antiderivative differs from another by a constant, and that constant will be subtracted when you take this difference. Okay, but don't worry if you don't get that. It just works for any antiderivative. The right hand side, you can put any antiderivative you want into this formula. So you might kind of be like, maybe I should say, like, why is this useful? So why is this useful? And we'll see examples of this in a bit. So suppose we know the velocity of an object, v equals v of t of an object, as the object travels from time t equals a to time t equals b, right? So then we know, then we also know, then we suppose, okay, and we want to know, what do we want? So we know the velocity, we are observing the velocity, and we want to know how far the object has traveled in that time period. That's what we want to know. Okay, well then, note that the derivative of position, so remember s of t, if s of t is the position of the object, of the object at time t, right, then the derivative of s of t, we talked about this a long time ago, is the velocity. So turning it on its head, another way of saying this is that the antiderivative of velocity is position. So the antiderivative of velocity is position. Okay, so therefore, by the definite integral, by the definition of the definite integral, we have the integral from AB of the velocity dt equals the value of the position at the time B minus the value of the position at the time A, is this other crazy notation, S of t B minus A. And this difference, this difference here, right? This is the net change in position or the velocity, sorry, or the displacement of the object. That's often called the displacement. The net change in position in physics is often called the displacement, or the displacement of the object. And that's exactly how far the object has traveled. So, i.e., how far the object has traveled. Has traveled from time t equals a to time t equals b. Okay, so and what we're going to see is that we can compute, so we can get, if we know the velocity using this definite integral tool, we can get the distance the object travels, right, from time t equals a to time t equals b. And this quantity here, this definite integral, we can compute by computing any derivatives, like using the reverse power rule and all these other things that we discussed in the last several videos. They work for definite integrals just as they work for indefinite integrals, right? Because what does this result say, right? We just kind of, take an antiderivative at b minus antiderivative at a. We can compute the antiderivative, in this case is the position, using our knowledge of antiderivative formulas so far, and then we can there'll be we have properties of the definite integral that are very, very similar to properties of the indefinite integral, and we can use that to figure out this values. Okay, so let's do so. Before I actually do an example of dealing with position, let me just kind of just remind you of some basic properties, do some basic examples, and then we can do an actual physical example, and we'll do an economical example too. But first, I want to just warm up in some sense, because it's a little bit of a different thing than doing the indefinite integrals. So we can compute definite integrals in much the same way we do indefinite integrals. In fact, definite integrals satisfy many of the same properties. Okay, so for example, we have sum in constant multiple properties. We have some difference in constant multiple properties. So it'd be the integral from a to b of f at x plus or minus g at x dx is the integral from a to b fx dx plus or minus a to b g at x dx. And that's the, we had the same property for indefinite integrals. Like this, remember if you the antiderivative, the sum of two functions is the sum of the antiderivatives, same thing with the difference. And this is the same thing for this definite integral net change gadget. It follows exactly the same rule. And we also have a constant multiple rule. So if k is any constant, we have the integral from a to b, k f at x dx is k times the integral from a to b f at x dx. Okay, so the definite integral of a constant multiple function is the constant multiple of the definite integral. And you can, if you really want to, you could prove all these things using what we know about indefinite integrals. They're of course related to indefinite integrals because they both involve any derivatives. And so using our knowledge of how any derivatives and indefinite integrals worked, we could prove these things if we wanted. We will not do that in this class, but there's not like it's a completely different type of thing. It's really the same phenomenon we saw before in a slightly different context. That's all. Okay, so let's just do some boring computational examples to kind of warm up with these, and then I will do some physics example and an economics example, and then I'll have to do a few more things that are a bit abstract that can come up in weird places, but hopefully you won't see it too much. So some examples. Okay, so evaluate the following definite integrals. So the first one we're asked to do is integral from 1 to 2 minus 3 over x squared dx. And the second one we're asked to do is the integral from 4 to 9 of the root of x plus 1/2 minus x. Oops. Dx. Okay. So let's do the first one. Oh, well, maybe just remember the formula because it's way up in the other thing. So recall definition. So the integral, the definite integral from a to b of fx dx is, let me write it this way, capital F at x from b to a is f of b minus f of a. Okay, where capital F at x is any antiderivative. Of little f at x. Okay, so that's the definition, and that's what we need to apply here. Okay, so any antiderivative works. So you just pick your favorite one, like I was saying earlier. So the first one, integral from 1 to 2 minus 3 over x squared dx So you pull out the -3. That's the constant multiple rule, just like we had before. So I can put that in parentheses in the margin. Okay, and so then, okay, now we just need to compute an antiderivative of 1 over x squared. So let me write, remember, it's easier to reverse the power rule if we write it as a single power of x for the negative number. So now, so we have -3, the definite integral from 1 to 2 of x to -2. And according to our formula, there it is up here, right? That gadget is just any antiderivative of x to -2, then we take the difference from 2 to 1. So -3, any antiderivative of x minus 2, well, we just use a reverse power rule formula. Just, we saw how to do that. We just add the 1 to the exponent and divide by that number to reverse the power rule. All right. And now, okay, now here you got to be careful with parentheses, because this -3 is multiplying everything. It's multiplying this entire definite integral. So we need some kind of parentheses or brackets around this quantity, and you'll have to expand the -3 throughout in the end. So this is -3. Okay, so let me just clean this up a bit. So it's x to the -1 over -1. So it's minus x to the -1 between 1 and 2. So it's -3. And then watch the negatives here as well. So minus 1 over 2 minus 1. Okay, so the value at the bottom limit gets subtracted, right? That's what this little gadget does. Are you subtracting the bottom limit of integration, the lower limit? So it's minus and minus, so be careful. It's a common mistake. People forget to subtract. So it's -3 minus 1/2 plus 1. It's -3 times 1/2. It's -3/2. Okay, so that's our first definite integral done. Hopefully you're somewhat happy with this. Okay, so you may have to take some time to digest it. Again, remember that in this gadget, the top limit, you just plug it in. The bottom limit, you got to subtract it. So we're actually subtracting a negative thing, so you end up adding it. That's all to be aware of there. Let's do another example. So the second example we wanted to do was the definite integral from 4 to 9, the root of x plus 1/2 minus x dx. And, I can also just simplify this a bit. Well, I'll write it as x to the 1/2. That makes it a bit easier to reduce the power, to reverse the power rule. Now we can use our sum difference rule. So for definite integrals, so 4 to 9, x to the 1/2 dx plus 1/2, the integral of 1/2 from 4 to 9 dx minus the integral from 4 to 9 of x dx. And these are all fairly easy antiderivatives, right? Each piece is quite easy. So we do this power rule thing, +1, reverse the power rule, +1, evaluate it at 9, subtract the value at 4. Now the antiderivative of 1/2 is, remember, half is 1/2 x to the 0. So we reverse the power rule, you add 1 to 0, you get 1. So the antiderivative is 1/2 x between 4 and 9. And this one we've seen many times. Between 9 and 4 again. So I need a bar here. Okay, and remember this negative, like I was saying earlier, this negative has to distribute the entire difference throughout the entire difference, so be very careful with the parentheses. Okay, so 1/2 plus 1, I'll write another line, I guess, but this is fairly straightforward. This is x to the 3/2, right? You have 1/2 plus 1 is 3/2 in the denominator becomes 2/3. And you bring it up to the numerator. So between 9 and 4 plus 9 over 2 minus 2 minus 81 over 2 minus 4 squared is 16 over 2. Okay, now that negative, like I said, that negative's got to multiply everything. So keep these parentheses intact. And this you can evaluate. So this is 2/3 times 9 to the 3 halves minus 2/3 times 4 to the 3 halves. I mean, you could at this point use a calculator if you want. Okay, you can evaluate these rational exponents by hand fairly straight, in this case, fairly easily, but adding everything together and doing all the arithmetic is kind of tedious to do this by hand. So I'll just tell you what you get. If you put it into a calculator, you get minus 52 over 3. So use a calculator. Okay, so hopefully, I mean, the one thing about this is like, you get the hang of this pretty quickly, but some of the calculations at the end stage can be quite complicated. So that's one thing to keep in mind. Okay, now we can do some examples that involve applications, and hopefully this won't be so bad. I think the numbers in one of them get to be bad, but. Okay, so let's do the first example here. So a rock is dropped from the top of a 400-foot cliff. So its velocity at time t seconds after being dropped is v of t equals minus 32t. Find the displacement of the rock during the time interval t between 2 and 4, from 2 seconds to 4 seconds. In other words, find how far the rock traveled, the rock goes between 2 seconds after it's dropped and 4 seconds after it's dropped. It can be useful to kind of indicate a picture here just to see why the numbers are making sense. So here you are. You have this cliff. It's 400 feet. And you're dropping the rock. There it goes, right? And so the velocity is negative, so the position direction is actually negative. So the positive direction is actually upwards in this example, which is kind of weird because it starts, it has a negative velocity, right? So it's gonna, in other words, the displacement should turn out to be negative here. That is traveling in the negative direction. The upward direction is actually positive because we're giving it a negative velocity for falling downwards. Okay, so looks a little funny, but I think kind of setting up the coordinates, the positive direction being up, you see that, okay, the negative velocity means that it's falling down. And we should expect a negative displacement. So negative, how far it's traveled in some senses, it's going to be negative because it's in the downward direction. Okay, so let's do this. So we talked about, recall from above in my whole example is that if we wanted to find the displacement, we just take the definite integral of the velocity function, b of t dt. So that's s of b minus s of a, or s of t from time a to b. Okay, so this one's not too bad because in our case, okay, we have the a is 4, the bottom limit is 4, the lower limit of integration is 4, the velocity is minus 32 dt, right? And the top limit was, sorry, the bottom limit is 2, the top limit is 4, the velocity is minus 32 dt. And this is an easy antiderivative. We can take out the minus 32, 2 to 4, t dt. And the t is t to the 1, so you up the power, divide from 2 to 4, and you get minus 32. So now this is 4 squared is 16 over 2 minus 4 over 2. So that's minus 32. So that's 8 minus 2. So it's minus 32 times 6, and that works out to be minus 119, minus 192 feet. I clean this up a bit. So that's actually not, you can see like how the definite integral is very, very useful. And this is a very straightforward calculation. So from knowing the velocity, right, we can compute the displacement, or in some sense, like how far the object travels between 2 and 4 seconds, just by finding this easy antiderivative of t, which is t squared over 2, right? And then subtracting the value at 4 minus the value at 4 minus the value at 2, and then you just do some algebra. And I should be very careful with my parentheses here. There. Okay. And again, the answer is negative because the object is traveling in a downward direction. It's set up with a negative velocity. Upward direction is the positive direction. And this choice of coordinates, it looks a little weird, but if you draw the picture, it kind of makes sense. Okay, so economics example. Let's do an example from economics. So recall the cost function. C equals C of X is cost of producing X units of a certain thing, certain product. And the derivative of the cost function, so C prime of X is the marginal cost. And one kind of thinks of that as it gives you a way of estimating the cost of producing one more unit after you've produced X units. We talked a lot about this before the first test, maybe. So it was a while back. So in this example, we're going to try to figure out the cost we're going to start with the marginal cost. So it's going to be like the last example where we start with the velocity. So we're going to start with the derivative of the cost in this case, and then try to figure out something about the change in cost. Okay. So let me actually write the question now. This was just kind of a little review. Okay. So consider a marginal cost function. C prime at X equals 0.09 X squared minus 4X plus 100. So that's going to be our marginal cost. Find the additional cost incurred by the producer when production is amped up from 3 units 219 units. Okay, so let's actually try to figure this out. So what is it asking us to do? So we want to find the change in cost as we go from producing three units of goods of product, 219 units of product. Well, what is that difference in cost? Well, that's the cost, say, of producing 19 things minus the cost of producing 3 things, right? So this difference is just the following difference. The cost of producing 19 items minus the cost of producing 3 items, which we abbreviate in this wonderful bar notation, 19.3, which we recognize as a definite integral from 3 to 19 of the marginal cost, right? So the cost function is the derivative of the marginal cost is the derivative of the cost function. So again, like turning on its head, the cost is the antiderivative of the marginal cost, just like we did with velocity and position, right? So the cost, so hopefully you kind of saw that coming, but the cost function is an antiderivative of the marginal cost. Okay, so we can just to compute this difference of incurred in production, amping up production from 3 to 19 units, we can just compute this definite integral of the marginal cost. So all we need to do is compute the definite integral on the right-hand side here of the marginal cost. So we need to just compute the definite integral. Sorry, 3 to 19 of c prime at x dx. Now we were given what the c prime at x was, right? It was way up here. We're not that far up. There it is. That was our c prime. Okay. So I'll just put that here as 3 to 19. So it's 0.09 x squared minus 4x plus 100 dx. And now we can use our properties of integrals all over again. We're getting hopefully to be a bit pros at this. So we get the integral from 3 to 19, 0.09 x squared minus the integral from 3 to 19, 4x dx. Oh, I dropped the dx here. Let me fix that. This is a common habit. Bad habit. And then plus 100, 3 to 19, 100x, oh, sorry, no x, 100 dx. And we can use the constant, so that's just the sum and difference rule for definite integrals that I talked about a minute ago. And now we can do the constant multiple thing. So you could 0.09, 3 to 19, x squared dx minus 4, 3 to 19, x dx. That d looks like a 2. Let me correct that. Plus 100, 3 to 19, dx. Okay, and so now this is, if you want, I can say in the parentheses, this is just the constant multiple rule. And now we just, these are all like these guys here can all be computed by just using the reverse power rule, very standard antiderivatives. So we have 0.09. The antiderivative of x squared is x cubed over 3. Value at 19, subtract the value at 3, minus 4 x squared over 2. Before I do that, bar. The value at 19, subtract the value at 3, plus 100, x squared over 2, the value at 3, the value at 19. Okay, now unfortunately, this is kind of a bloody nightmare in terms of the numbers. So I'll write out one more step, but then you should just punch it into a calculator. So it's 19 cubed over 3, right? So the top limit minus the value at the bottom limit, so that's 27 over 3. So 3 cubed is 27. Close the parentheses. Minus 4, 19 squared over 2, minus 9 over 2, plus 100. Oh, sorry, this is messed up. This is just an x. Right, there's just 1 dx. 119 minus 3, that one's the easy one. All right, so when I look back up here, I think I mistook the x here, the dx here for an x. So it's just 1, and the antiderivative of 1 is just x. Okay, so this is the whole thing. What do we get? So this you should just punch into the calculator at this point. Try to do this by hand. I'll totally screw it up. And when you do that, you get that this is $1,196. So remember what was it that we were computing here? This whole mess, right? Go back up to the top. We were using this definite integral to compute the difference in the cost. How much more? What additional cost we would incur from amping production up to 3 to 19 units of fun stuff. So we should have a statement to that effect. So C of 19 minus C of 3 is $1,109.96 is the additional cost that we would incur by amping up production from 3 units to 19 units. So that's another case where definite integral can be extremely, extremely useful for us. Okay, excuse me. So I should mention there are 2 kind of more properties of definite integrals that at times can appear useful. They're not as commonly used in applications as the ones we've used so far, but I would be remiss not to mention them. They do appear on the homework, so I should mention this. So 2 kind of less common properties of definite integrals. Okay, so one is this switching limits of integration property. Okay, so this is actually really easy to see. So if you do the integral from a to b, f of x dx, by definition, that's f of b minus f of a, where capital F is any antiderivative of little f. But that's the same thing as when you factor our negative, saying f of a minus f of b. But that's the same thing as saying the integral from b is the bottom limit to a is the top limit, f at x dx, with a negative out front. So that's what that's doing. Okay, so this whole thing, this little silly computation is just to say that if you switch the limits of integration, you have to introduce, you switch the bottom and top limits, you have to introduce a negative sign. So this is the switching limits property. And the other one is integration over adjacent integral over adjacent intervals. So the integral from a to b f at x dx. If we integrate from a to b and we integrate from b to c and we add the result together, that's the same thing as integrating from a to c. So it's kind of like if you take two integrals, which are in the intervals kind of one integral from a to b and the other from b to c, and you add those integrals together, you get the integral of the whole thing from a to c. That's how to think of it. It's easy to show this by just, I mean, if you wanted to do two, I could do it in gray here. So this is just like f of b minus f of a plus f of c minus f of b. So this guy is this guy is this. And you see that the f of b's cancel. And you just get f of c minus f of a, which is exactly this thing on the right-hand side. So these are not, once you write out what the definition of the definite integral is, it's not at all surprising that these things are true. But it's not like something that you would think about as coming from the indefinite integral, because there's no analog of these properties in indefinite integrals, because you're not talking about limits of an integral in an indefinite integral. Whereas the first two properties, right, those were just the properties that kind of are brought over from indefinite integrals to definite integrals. These are something unique to definite integrals. They can be useful in certain situations, but the situations tend to be rather abstract. So I can kind of do one thing like this, and you can play with more on your homework. They get a bit dry after a while. So here's an example of using these properties. Okay, so suppose we're given that the integral from -3 to 2 f at x dx is equal to 10, and that the integral from -3 to 6 f at x dx is equal to 15. And we want to find the integral from 2 to 6 fx dx. So like I said, this is rather abstract. It's not obvious where this would come up in applications yet. And you probably won't see it in an application in this course, but it's kind of good to keep it in mind. Okay, so maybe it helps in this case to draw a bit of like a number line picture to see what's going on. So what we want is we want something from 2 to 6. We want this integral from 2 to 6 here. And we know something about the integral from -3 to 6. So we know everything going out to -3. So we know this integral And I won't, well, I can put the F here. Okay, so we know that integral. And we know also the integral from -3 to 2. Okay, and so this is the unknown thing. So this is unknown. So you can kind of see now how drawing this out, you see how I patched together. You can see the two intervals that are kind of patched together here. Different color. So you have this integral -3, 2, the two adjacent intervals, -3, 2, and 2, 6. And that, from the adjacent interval property, where did it go? Right? If we take the integrals over adjacent intervals and add them, that's the same thing as just looking at the integral where you've stuck the two intervals, the two adjacent intervals together, right? So by the adjacent interval property, this integral plus this integral will give you the whole thing, the whole integral. Now, we don't know this one, but we know these two. And so that adjacent interval property will give us an equation where we can solve for this. Okay, so that's the idea. And so if the picture helps you, great. If it doesn't, then you can just look at the formula for the adjacent interval property. I don't like personally staring at formulas, excuse me. So you just need to kind of figure out if you're like much more geometric person, maybe you like drawing a number line like this and seeing how the pieces fit together, and then how to apply the formula from there. Okay, so by the adjacent interval property, we have that the integral from -3 to 6 f of x dx is equal to the integral from 2 to 6 fx dx plus the integral from -3 to 2 fx dx. And I guess maybe I should write it the other way to be consistent with the formula. So first do -3 to 2, and then do 2 to 6. Again, the order in which you add things doesn't matter, but to be consistent with the formula, the lower interval usually comes first, and then the higher interval, the greater interval. Okay, and so we know this, right? This thing is equal to, we were told above what it was, right? That's equal to 15. This is equal to 15. We were told that, so this guy is 15. We're told that the -3 to 2 is 10. And then we want to find that. Find the one in pink, right? Here. Right? So this is equal to 10. So we get the equation. So applying the known values, we get the equation. (15 = 10) plus the unknown integral 2 to 6 fx dx. And so this is 5 equals the integral from 2 to 6 fx dx. And that's, so 15 minus 10 is 5. And so then we've got the value of the unknown integral. So we found the value. So that's kind of like how you go about using that kind of a property. And sometimes you may have some limits going the wrong way when you play this game, and then you'll have to use that, switch the limits property and introduce a negative sign somewhere. That doesn't happen in the examples I kind of came up with. It may happen on the homework, so just be aware of it, and it's something I'm willing to discuss in a live meeting. Okay, so this turned out to be a lot of material for this week. So it turned out to be 2 long videos and a kind of shorter video. It looks like, from what I can tell, they've stocked up, they've put a lot of material into the last few weeks. So the videos might be a little longer, but then the last 2 weeks of semester, we don't have any videos. So that's a plus. All right, thanks for tuning in, and I'll see you in the live meeting.